Teleoperation is a widely used paradigm to deploy robotic systems in dangerous or difficult environments, ranging from underwater exploration to disposing of toxic, explosive and nuclear materials. This study looks to investigate sensory feedback methods within teleoperation scenarios. While camera feeds within teleoperation are typically available, additional tactile information is paramount to successful and efficient manipulation. Although sensory feedback methods within teleoperation is a well-studied area, it became clear while reviewing literature that a large majority of previous studies focus solely on time of completion as their main assessment metric. This study looks to further this by assessing sensory feedback methods from the scope of multiple assessment criteria. This was achieved by looking at two specific feedback methods, vibration feedback and visual cues, and applying these to multiple tasks that ranged in complexity. These were then assessed in relation to time of completion, error rate, and perceived workload, which used the NASA TLX. NASA TLX is a widely used assessment tool that measures the perceived workload of a particular task. By using the NASA TLX, allowed insight into the discrete effects of the feedback methods themselves. The contribution of this paper is the empirical findings that clearly challenge the dominating role that time measurement has in current methods. At the core of the study was a teleoperation task, where the operator used a semi-humanoid robot and a camera feed to teleoperate in the remote environment. The video shows the operator's perspective, demonstrating the limited depth perception that was present. The sensing within the teleoperation system was made up of tactile sensing and proximity sensing. The tactile sensing consists of piezo-resistive sensors mounted on the inside of the gripper. These sensors dealt with the contact interactions with objects in a remote environment. The proximity sensing consisted of an ultrasonic sensor mounted on the underside of the robotic arm. This provided the operator with distance information relating to the remote environment. This sensory information was provided to the feedback methods consisting of visual cues and vibration feedback. Visual cues being a graphical representation of the sensory information collected in the remote environment. Vibration feedback consisted of disc motors mounted on a metal band fixed to the operator's arm. There were 2 bands for tactile feedback and 2 bands for proximity feedback, as shown in the diagram. In order to get accurate and reliable results from the study, it was imperative to have a clearly defined test scenario. A board with zoned areas was developed, allowing objects to be moved and manipulated within a measurable space. Each participant undertook 3 tasks, starting with a simple pick-and-place task and ending with a complex parallel bar task, requiring a high level of control. Due to this fixed ordering, along with 3 feedback method conditions, no feedback, visual feedback, and vibration feedback, there were 6 permutations required in relation to feedback ordering. Participants were randomly assigned into one of 6 permutations. This allowed for the dataset to be looked at as a whole and not relating to a specific task. Due to participants being untrained, it was important to use familiar objects. These objects ranged in shape, size, weight, and level of deformation, adding a level of complexity to the task. This video shows a participant undertaking Task 2 in the study. It also shows the feedback presented to the operator whilst undertaking the task. It provides an insight into the proximity and gripper feedback acted upon in the remote environment. The operator lowers the arm, which activates the proximity feedback. This notifies the operator of the position in relation to the table. The operator then maneuvers the arm towards the object. The gripper feedback is activated, indicating a touch of an object, but not a full grip. The operator then readjusts the arm's position to maintain a secure grip of the object. The object is then released in the desired location and the gripper feedback deactivated. The operator then approaches the next object, where proximity feedback is activated. Again, the gripper feedback is activated, indicating a secure grip. The object is picked up, and manoeuvred to its position. Proximity feedback is not activated due to the arm not being close enough to the table. The object is then dropped, and due to this, the task is failed. The study itself was made up of 24 participants who undertook all 3 tasks 3 times. There were 17 male and 7 female participants with an age range of 21 to 63 and an average age of 27. As previously explained, each participant was put into one of 6 feedback permutations, which allowed us to look at the dataset as a whole. Initial data analysis looked at task completion times unrelated to feedback methods. All 3 tasks presented a learning curve, although task 1 and 2 were found to be significant. This was in line with the original hypothesis, which stated participants will complete the task faster on their 3rd and final attempt compared to their first attempt. Due to the participants being untrained, this was used to assess any learning curve that was present and had potential impact on later results. Task completion times was further investigated, with results indicating no significant findings with the additional feedback methods. Contrary to predictions, the integration of all feedback methods had no significant impact on the overall completion time of the task. This is shown by the inconsistent median values across all 3 box plots. Furthermore, there was no conclusive results presented in relation to the reduction in error rate. This was for both the vibration feedback and the visual cue conditions. The main chart shows the total errors across all tasks, with the 3 charts on the right hand side being the breakdown across task 1, 2 and 3. Another way to look at this is look at the average errors per run in relation to the feedback methods themselves. On average, there was an error rate of 1.88 per run for no feedback, 1.22 per run for visual feedback, and 1.53 per run for vibration feedback. Although only partially conclusive, the addition of visual cues shows a reduction in error rate across all 3 tasks. This implies a trend, but not found to be statistically significant. The most conclusive results can be found in relation to perceived workload. 22 out of 24 participants presented a lower perceived workload with the addition of vibration compared to the no feedback condition. 18 out of 24 participants presented a lower perceived workload with vibration compared to the visual cue condition. This is a considerable finding. The individual tasks can be seen on the right hand side and present a considerably lower median with the vibration condition compared to the visual cues and no feedback condition. These were statistically tested using a binomial test, and although visual cues indicate a lower perceived workload across all tasks, this was found not to be statistically significant. This confirms the original hypothesis that vibration feedback would lower the perceived workload irrespective of the task. It also confirms a hypothesis that vibration feedback would lower the perceived workload compared to visual cues. With the reduced perceived workload, it is possible to make the recommendation of vibration feedback for prolonged teleoperation tasks, or teleoperation tasks that require a high level of concentration. Although currently not found to be statistically significant, the results in relation to visual cues point towards a reduction in error rate. From this, we were able to make the recommendation for visual cues being used in teleoperation scenarios that require a high level of accuracy. Overall, the study has highlighted the need for broad assessment criteria. The impact of feedback methods in teleoperation should not be investigated solely in terms of time of completion. Although for specific tasks, particular metrics should be analysed, the study highlights the need for a broad assessment criteria. This study has utilised perceived workload and error rate alongside completion time, which has allowed us to uncover much more subtle implications of feedback other than time alone. The learning curve presented over time demonstrates the meaningfulness of time of completion measure on our tasks. However, no difference was found in between tasks. This further demonstrates that teleoperation studies should not solely rely on time as a measure of success. Thank you for listening.